Right, so everyone please be seated. Oh, it's okay. We'll get the attendance first.
Oh my god, I didn't know like
3 periods of 10. Smells good.
Does it?
What's that smell? The seltzer? You know this?
So then you will think oh, it smells like that.
What is it? Can you come back to it? Right away.
No, it smells too.
Everybody needs to listen.
Let's go.
Sir, wrong class.
Yeah,
It's
no,
from
I'm not
money.
here.
We did.
Oh, sir, yes, sir.
Oh, right, right, right.
One guy didn't see
Sir, you
That
can
should be. Can you please get yourself and if you're not part of the chemistry class. If you're not part of the chemistry class, please fetch yourself and leave now. I just saw him outside.
He has a basketball. Who? James. James has a basketball.
So we have three students on here. So can I have the number? I think
120, 41.
41.
5B number.
41.
I mean 5B1.
51.
Yeah, yeah. Not 20. Keep
Sir,
me.
sir.
Keep me.
41.
41 seconds.
20.
Sorry, not asking.
Yeah. Can you please leave now if you're not part of the chemistry class? Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 15. So we have 15.
Wait, it's good.
James. He used to be sitting there.
Yeah.
Okay. So we have 4. Can everyone please be seated? Can everyone please be seated, especially the students at the back? Can we continue? So right, okay, so record. So last time we finished discussing a few different types of addition polymer. Yeah, okay, so please. And we we discuss their uses, okay? And we stop abruptly at the polystyrene, okay? So polystyrene, it comes in two different forms, okay? Just like we have two different types of PVC, we have the plasticized and unplasticized PVC, and we also have two types of PE, the LDPE low density polyethylene and the HDPE high density polyethylene. Now, with PS, we also have two different types. We have the expanded polystyrene. So can you open the sign? We have two types of PS as well. Okay, and they are number one, expanded polystyrene, also known as styrofoam. Okay, so all of you know styrofoam. What are we using to expand this polystyrene? We're using some gas, some inert gases like nitrogen to expand the styrene, okay, to the polystyrene. So this is also, right now, also known as styrofoam. What are some useful properties of styrofoam?
Food boxes.
Yeah, but what makes them suitable?
It cannot receive.
Yes, they are good insulator, in other words. Okay, so right now this very unique property of expanded polystyrene, they are insulators. Yeah, so they are good insulators, so therefore useful as lunchbox or any of those disposable lunchboxes. Okay, but this is very bad for the environment because just like any other type of plastic, they cannot be broken down by bacteria. So they will just stay there like
How long does it take for it to be affiliated?
well, technically they don't break down. So when you see them break down, it's just that they are breaking down into smaller pieces. But if you add up all those pieces together, they still add up to the same mass. Okay, so technically they don't break down.
So they're eternal.
Yeah, but recently, I think in Japan, okay, they have discovered a strain of bacteria, okay, that they can eat styrofoam. Okay, they can eat styrofoam. Okay, so this is rather encouraging. Okay, so you can look up more about that genetically modified bacteria, which can eat like plastic. Okay, so and then we have the unexpanded. So the unexpanded polystyrene. Know the appearance of these two types of polystyrene. The first one, the expanded polystyrene, they appear white in color. So anyone who have used the disposable lunchbox will know, okay, they are white and opaque. They don't let light through. Okay, that's what opaque means. And the unexpanded polystyrene, they are transparent. So for those of you who still have those CD jackets, okay, those CD boxes, okay, they are transparent. And this material, it is PS, the unexpanded one. It is fully transparent, okay? So that's PS as well. Yeah, I wouldn't say it's regular plastic, because all plastics, they are made of C and H's. Just because they are all made of C and H's doesn't mean that they all behave the same way, they all have similar chemical quality and physical. No. This is the thing that makes the CD, what do you call it? The CD box or something. I don't know what you call this. It is the CD box. You put the CD in it, and you can see the album art on it. Yeah, we used to.
It's ancient.
Yeah, it's ancient. If you know this, you have exposed your age. Yeah, so this is PS. Everybody use, digital, MP3, something like that. We don't use physical disc anymore. Yeah, VHS even more ancient. Okay, even more ancient. So can you go down? Unexpanded polystyrene, this is transparent. Okay, so they are pretty hard. Okay, so they are pretty hard. Yeah, so they are hard, and they are used for different applications. So the expanded polystyrene, they are used as the styrofoam cup. Okay, so in the styrofoam cup. The reason why they are good insulator is because when you zoom in, there is a lot of what trapped inside. Air. Yeah, there's a lot of air, pockets of air trapped inside, and air itself is a pretty good insulator. So these are pockets of air, and we can create the expanded styrene by blowing air of blowing gases into unexpanded polystyrene. Okay, so here is a quick look at the manufacturing. So manufacturing of the expanded polystyrene. So first of all, we'll need the monomer, which is styrene. Okay, we polymerize it by addition polymerization. So remember we have addition, polymerization, right? Addition polymerization. It will then turn into this structure. So remember that hexagonal ring from last time that looks like a Z base? Yeah, that's the benzene ring. And if you refer to this as the benzene ring, the whole thing we refer to it as the styrene monomer. Okay, this is like a single Lego block. If you have many of the same Lego block, okay, attached end to end, you will have the polymer, polystyrene. But then this is just the unexpanded one, okay, the unexpanded type of polystyrene. You will have to blow some inert gases. Can anyone tell me what's the alternative word for inert? Inert means unreactive or stable. Okay, yeah, so you add inert or unreactive gases. Okay, inert, INERT, inert gases. Some examples are nitrogen, nitrogen gas. Okay, you can blow nitrogen gas, which is pretty abundant. How abundant is it in the atmosphere? 78%, 21% oxygen. Okay, yeah, then it will turn into this, like expanded polystyrene. So the polymeric structure is actually the same. So you still have the styrene. You can simplify this into a single thread. In polystyrene, you will just have them stacked on top of one another very, very tightly. But when you blow these inert gases, okay, unreactive gases, into the polymeric structure, what you end up getting is like these many gaps in between. So you have these pockets of air inside the structure, okay, and this will be what expands the polystyrene into expanded polystyrene. So is that clear? No, they're just, the air is flowing in randomly. Yeah, and then now this will disperse the polymeric fiber. Each of the threads you see here represents a polystyrene, okay? Each of these threads you see here represents a very, very long repeating unit of this. Okay, you have many of these repeating units in a single thread. And because you have many of these polymeric strandings to one another, when you blow gases in, okay, it reduces the density. So this is why when you cut out a piece of styrofoam and you put it on water, they always float because there's air inside. Yeah. But then for this CDBs, you can put it in water, maybe it won't float because there isn't as much air inside. It is much denser as a result. So you can see we can influence the property, for example, density of a polymeric substance just by adding air or removing air, so we can change between these two forms depending on the use case. So just put down the two different types of polystyrene we have. And last but certainly not least, we have perspex. Okay, so perspex. Every time you go to the lab, remember last time we go to the lab, we wore safety goggles. The safety goggles is of course not made out of real glass. Okay, because when real glass shatters, there will be a lot of sharp debris. Okay, like that will instead of protecting you, damages your eyes. So you have perspex. Perspex is made of the material methyl, 2-methyl. So right now methyl, 2-methyl propenoate. So propene. Mind your language, yeah. So methyl, 2-methyl propenoate. Does anyone remember how we named ester? Yeah, ester. E-S-T-E-R. No, never heard of it. Okay, I think maybe, I think I included that in the notes, okay, maybe not. So anyway, I'll draw you the structure. So we have CCC. What does pro mean? 3. You can try all the numbers. 3. Remember, minions eat, killed, banana. P is the third one. Okay? So 3. Just remember minions eat, killed, banana. Minions eat, killed, banana. Okay? Yeah. Pants will be 5. Don't mix up probe with pants. Yeah, you know pentagon.
Yeah.
Okay, pentagon has 5 like sides. Okay, probe is a different word you don't see in mathematics class. Okay, so what does methyl 2-methyl propenoate look like? Okay, so we have this to be propenoate. Yeah, so propenoate, and you have methyl 2-methyl. So methyl 2-methyl propenoate like that. So you have a double bond at this position. Okay, so what exactly is each part of it? So can you put down the probes under the structure? So you have 3 carbon, you see, 1, 2, and 3. So what does methyl 2-methyl mean? Okay, so methyl 2-methyl propenoate means this part. Okay, so you have methyl, and then you have, let me just put it this way, so you have methyl 2-methyl propenoate. Okay, yeah, I think I moved the group to a wrong position. So what does the first methyl describe? So the first methyl here describes this part. 2-methyl propenoate means along the propenoate chain. So along the, so this is the propenoate chain. So you have the propenoate chain. Where is position 2 on this propenoate chain? Is it a carbon? There are 3 carbons I highlighted in yellow. So is it the one on the left, the one in the middle, or the one on the right? The one with the double bond. Well, there are 2 with double bond. Okay, you mean the one at the center. The one at the center. So this is position number 2, because we are counting it from this direction. So 1, 2, 3. So we have 2 here. Okay. So 2-methyl. Where does the second methyl group go? The second methyl group goes in this position. So you have another methyl group here. You remember methyl group means CH3, right? Yeah, so CH3. So this is methyl 2-methyl propenoate. So how can this thing undergo polymerization? Do you remember what we need to do before we can draw the repeating unit? Is that we need to arrange which group front and center. Which of the groups must be put at the center of the stage? The CC double bond. So why don't we do the same thing here? So can you write down the question? My question is, given that this is the monomer that forms perspex. Okay, so this is the monomer for making perspex. Okay, can you show me how this monomer can undergo additional polymerization? So show how the monomer shown on the left can undergo addition polymerization to form perspex. Okay, so to form perspex. Perspex is a lot easier to remember than what? Than polymethyl 2-methyl propenoate, right? Yeah, so if you have to pick between these 2 names, you will pick perspex any day over this very, very long name, right? But this is polymethyl 2-methyl propenoate. It means perspex, okay? So for, oops, let me copy this onto the side. So you have polymethyl 2-methyl propenoate, aka perspex. So this thing we can substitute as perspex. So how do we do that? First of all, yeah, maybe here's a quick warm-up first. Remember how I said if you have C3H6, you need to first show the double bonds. Okay, what does it mean when you have C3H6? Is it an alkane or is it an alkene? And how do you know? It is an alkene. Why is that? Because it fits which general formula? CnH2n instead of CnH2n plus 2. Because when you put n to be equal to 3, 2n will just be 6, right? If n is 3, 2n is 6. So if you add another 2 to that, it will be C3H8, which is not what we see in here. This is an alkene. So we put 3 carbons, and an alkene must have a double bond, right? So we put a double bond somewhere. It doesn't matter. You can also put the double bond here if you like. It won't affect your answer, trust me. So once you have drawn the structure, you have to decide how many H's go to each carbon. So how many H's go to each carbon starting from the left, most carbon? 3. Which rule are you using to come to this answer? Carbon must form 4 bonds. So the first carbon has 3 H's. What about the second? 1 H. What about the third one? 2 H. So now you can figure out where you know when you see C3H6, you want to know where the 6 H's go. These are where the 6 H's go. Okay? And then you need to put the CC double bond at the center stage. So can you do that now? We have the CC double bond in this position. We have the CC double bond in this position. Turn them both into a structure with the CC double bond at the center of the stage. I want you to show me what are put on the 4 corners. At the 4 corners. So maybe let's do this easier one first. Just warm up your brain. Okay. So how many? What do we put on the top left hand corner? NH. Yes. So there's an H. And then what about the bottom left hand corner? CH3. What about the top right corner? H. What about the bottom right corner? H, right? Yeah, so this is how you go from here, well actually go from here, from C3H6 to here, to here. You see what to do? Okay, yeah. In exam, they will just try to hide everything from you and they will just say, here's C3H6, draw the column. Well, you need to figure out what C3H6 looks like by going through these steps. Okay? Yeah, let me just put down that rule once again. Carbon must form 4 bonds. It is because of this rule that, so use this rule to figure out where the hydrogen goes. So to figure out where the H will go. Okay? Now that this is done, you know there's H, CH3 here. Yeah, CH3. Okay, maybe this is where you ask the question. Why is it H3C? Why am I not writing CH3? That's because, is it the carbon or is it the hydrogen that gets directly attached to the C? Carbon, yeah, so it will be better that you write H3C as a result of that. But it's okay, in DSC, because in exam they will show you H3C and I don't want you to look at it like you haven't seen this thing before. This is just the mirror image of CH3. And we tend to write it this way, not because we like things looking weird, but because it is the C that actually bonds to this C, right, you see. It is not any of the H's. So, but in DSC, it's okay in your answer that you write CH3. Anyway, let's do this for naphtha, 2 naphtha propanoid. I want your help again. Tell me what I should put at the 4 corners. Top left. How many H's are there? I did not show. 2. Yeah, there are 2 H's. You can put them in any position. Okay, I mean you can point it at 10 o'clock, 8 o'clock position, or 12 o'clock. Doesn't matter. Yeah, and then all the hydrogens they are in place. So can you tell me, by looking at this diagram, what are the 4 groups at the 4 corners, starting with the top left? H. This is an H. This H is the same H as this one, right? And then the bottom left? H. Yeah, the top right? Yes, bottom right? There's a lot of figure here. Yeah, or COCH3. You can condense it further as CO2CH3. Great. And finally, what do? We write out the polymer structure. Remember the modification we can make? Change double bond to single bond. Add 2 new bonds. Yeah, add a bracket and draw another 2 bonds on the side. So very good. So now you know. In this single chapter, yeah, you will just be assessed on the same scale, okay, converting unknown structures into this form, yeah, with the CC double bond occupying.
This will be right, CO2.
Yes, but as you will find out later, we will try to write as COOCH3, okay. If you write it as CO2CH3, it kind of gives the impression that the 2 O's are attached to the same C, which they are not here. Okay, yeah, you see, well, yes, the C is connected to 2 O's, but it is one of the O's that get attached to the CH3. Yeah, so this is just to avoid those confusion. Yeah, but it's okay, technically it's okay. So you put HCH3, COOCH3. And don't forget to put an N on the outside, like that. Okay, this is Perspex. It is fully transparent and it's shatter-proof. Other than in the lab, when you look at the headlamp of the car, you know the car has a headlamp, right? Yeah, that you may think is made of glass. It is not. It's made of Perspex. So Perspex is what we call like some plastic glass or plexiglass. Plexiglass. They don't shatter like glass. Okay, if you really hammer the glass, it will shatter in 1,000 pieces. Perspex, they are safer. Okay, so and they are though not as strong as glass, they are useful in applications where glass is used. Okay, like goggles. Okay, that they provide the same optical clarity, similar optical clarity with glass. So for the bottom one, we will not go through this in detail. But I want to ask you one question to see if you can apply and think. Okay, so can you draw the polymeric structure? HCH3 and H. So and you have right hand. My next question is, can you draw, okay, a section of like a polymer formed by ethene and propene with 6 carbon. Yeah, with 6 carbon. Okay, so now I'll give you the structure, okay, and you tell me what the answer is. So the monomer, ethene and propene, what do they look like? So ethene looks like this. And let me copy this. Propene looks like this. H. You can put the CH3 anywhere you like, not necessarily at the top right corner. You can put the CH3 here, here, or here, as long as the other 3 groups remain hydrogen. It really doesn't matter, you can just rotate this molecule however way you like. It will still be the same one. That means the CH3 can be put on any position, not just here. So this is ethene. If this is propene, can you tell me what would the polymeric structure look like when we do those modifications? We'll do the same thing, right? Yeah, but do you see the question? Draw a section of a polymer formed by ethene and propene with 6 carbon. Can you look at this monomer and tell me how many carbon do you see per monomer unit? 2. So how many of the monomers should you draw if you were asked to show a section with 6 carbon? 3. 3, because 2 times 3 is 6. Yeah, so now let's do it. We have CH2, CH2. You see the question demanding for 6 carbon, and you have only 2 carbons per ethene. That means you need to draw this 3 times in order to show 1, 2, 3, 4, 5, 6. Do we all agree? Yes. Now what about propene? Tell me again, how many carbon does a single propene have? 3. So how many times should you draw propene if you're asked to show a section of polypropene with 6 carbon? 2. 2. Yeah, not Spanish.
Sir, do you know Spanish?
A bit. But just a bit. Maybe just the word Spanish, nothing else. Okay, yeah, so you have C, C, and then you have H, 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 CH3. Yeah, so that's what I'm asking. You have to be careful. Yeah, because I've noticed that more recently, because they know students can draw this. I mean, who doesn't know how to draw this? It's just like change double bond into single bond, right? If you do enough exercise, everybody can figure this out. But then they want to trick students, yeah, by asking you, oh, can you just show a section of polymer with 6 carbon? If you don't think, if you just draw this, you're not following the instruction. You're not showing 6 carbon in this structure. Which is why sometimes they will change the question like this, and you have to think how many times you have to draw the polymeric unit of propene in order to show 6 carbon. We can count 6 carbons in both cases, right? So you see what I'm saying? Okay? Yeah. So that's the answer. Okay, and something that I want you to watch out for. So next up, we have a very quick summary on all the plastics that we have learned this far. Okay, and we'll move on to the next topic, microscopic world 2, after this. and then we'll have the test.
Sir.
We don't have the book.
You,
You use one. Oh yeah.
do you need one? If you're asked to draw just a section of the polymer with 6 carbons, you don't need the bracket, okay? However, you can, you have to add 2 bonds off the side. This is what you normally do, okay?
Sir, will it ever ask for like 7 carbons?
No, because it's not divisible.
So the maximum is 6.
So it has to be something that.
It can be any even number, I would say.
3, 6.
Yeah.
So that's 6.
But yeah, because you know in exam time it's gold, so they may not ask you to draw 10 carbons, okay? It's like punishing you. Oh, I won't be late again, I won't be late. It's like asking you to write, I won't be late again 10 times. No, okay, nobody does that, okay? So we have maybe usually 6 or 8 carbons, I would say, 6 or 8. It has to be divisible by 2 or 3. Depending on the monomer. If your monomer has 3 carbon, then whatever number they give you, that has to be divisible, by the number of carbon in your monomer. Okay? Right. So next up we have the summary on, and then next week we have the test on organic. Yeah, we need to have a test on organic. So summary on addition polymer. What is that? So addition polymers, yeah, can normally wake her up and wake everybody else who is sleeping up. Nobody sleeps, okay? And yeah, I don't want you to do poorly in the test. So if you sleep, okay, not, okay? Yeah, so summary on addition polymers, okay? We have discussed quite a few, so just put that down. We have polyethylene. So polyethylene is from ethene to this. Okay, so maybe I'll just copy this. So n times that, and it will polymerize into something that looks like this. Yeah, and then you have the bracket and then the N on the outside. So we're going to copy this a few times. Okay, you need to write this a few times. So for polyethylene or PE, there are 2 types. They are LDPE and HDPE. So we have PE. So there are 2 types. LDPE and HDPE. Every time you have like 2 or more types of the same polymer, those plastics, they have different properties in those 2 different types. For example, for PE, we have HDPE, which is harder and has higher melting point. So higher melting point. So this is why they can be used to make drinking cup, okay, plastic drinking cup. And then LDPE, they are softer and they have lower melting point. So just draw some plastic objects made out of each type of plastic. So you have the food wrap. Yeah, so food wrap that is made from LDPE, and you have the plastic cup. Okay, you use in parties. Okay, are made out of HDPE. So what else? We have also polystyrene, PS. Okay, so polystyrene, PS. So it's made from, we'll complete the polymer monomer structure at one go. Okay, let me finish writing those different textures. So for polystyrene, you also have 2 types. One is the expanded, one is the unexpanded. Okay, so the unexpanded one is transparent. So unexpanded polystyrene. It is transparent. Okay, an example will be the CD box or CD jacket, okay, or whatever you call it. And then you have on the right the expanded polystyrene, aka styrofoam. Okay, so aka styrofoam, so also known as styrofoam. Right, and for this one, okay, it is not transparent anymore. It is a white, like material that looks like foam, so that's styrofoam. It is a very insulating material. Okay, very insulating. So therefore, e.g., like lunch boxes. Okay, lunch boxes. Okay. So this is the CD box or something. Next up, we have what else? PVC. Does anyone remember the polyvinyl chloride, which is found in vinyl? This polyvinyl chloride. The nickname is, this is its nickname actually, PVC. Okay, the purpose is the method name is polychloroethene, and from that we can draw the monomeric structure. And this is PVC. Okay, so we have PVC, and this is PS, and that's PE. And just like the other two previously discussed, what is that? Plastics. For PVC, we also have two types. What are they?
Plasticized.
Plasticized and unplasticized. Okay, so which type is softer? Plasticized. Think about it. What does plastic mean? When you think of plastic, you think of something very soft, very and thin, things like that. So to plasticize something means to make something soft. So this is plasticized PVC and unplasticized PVC. Okay, so this is softer and flexible, right? Unplasticized PVC, they are harder, or you can just say they are rigid. Okay, and they are both opaque, right? Yeah, so they are both opaque. So the soft one can be used to make garden hose. Okay, yeah. So here, this is the garden hose used by the like the garden hose. Yeah. And then on the right we have the plastic pipes, right? Yeah, plastic pipes. So I think you can excuse yourself for the bathroom for now. But later nobody goes to the bathroom. You either use it now or you don't now. Okay. So plastic pipe. Yeah, and for the rest of you who want to stay here, you can first complete the structure here. Complete the structure here. And then we will check the answer with the remaining part. And you can put down a placeholder first. This is the beam, and that's polyethylene. Right, this is styrene, and this is polystyrene. And then we have yeah, we also have perspex left, but let me put that in here first. So we have this, and then this. Yeah, okay, one or two more. Okay. You can fill these diagrams first if you think you know the answer. Because after this part, we'll look at the next chapter.
You don't have a.
What do you mean you don't have a book?
It's
You
a
have
book.
It's another book. Okay, yeah, then you can choose to break that later. Yeah, but I don't really recommend, I don't really need you to break the book. Yeah, if you pay attention, then you don't need the book. Okay, of course, if you like to do some extra reading, you can do that. But yeah, we have. So this is. I think I didn't miss any of these functions. Yeah, I mentioned before. Of course, you don't have to remember all the properties. It's impossible. It's impossible to remember all the properties. This is why I just used one of those plastic objects to remind you of their properties. Like styrofoam cup. Everybody knows that styrofoam cup are very good at insulating heat. Yeah. I can't remember all these points. Neither should you. You don't have to. You just need to know a few hallmark features. Okay? Yeah. Like those way will do. Thanks. Okay. Oh yeah, you can take it now, or you don't have to. You can take it after classes. You can also do that. Any questions?
You want to just.
Okay, yeah, I think for the test, a few for the MC is they did a lot better in the MC. But in the long question, I would say like most of you will still have to pay attention more to the wordings in the question. Like for example, the first one. The first question asks you to write an equation for the reaction between copper oxide and sulfuric acid. But a lot of you, not just one of you, if I see only one of you, I will think maybe it's just carelessness. But many of you wrote CuSO4 as the reactant, which shouldn't be the case. Because the question is asking you to write the equation between CuO and H2SO4. That means these should be the reactant. Yeah. And some of you just wrote CuSO4 as the reactant. That's something to watch out for. Because it's built on microscopic world one. Yeah, this is built on microscopic world one, so you need to know like polarity. You need to know like the expanded octet structure. Do you know how to draw Lewis structure? What are Lewis structure?
What?
Lewis structure. Parallel before. Never. Okay. Well, actually, you have learned how to draw this in Form 3. Some of it.
I wasn't here before.
Okay, right. Okay, then don't worry. We'll just teach everyone from scratch. Okay, the Lewis structure. Okay, so hopefully the other students will be back soon. And for those of you who are back, help me complete these structures first. Okay, so later you can rest a little bit. Right, so yeah, why? Like, where do you want to go with that? You have a piece of paper. Are you feeling all right?
Another round of chemistry. Another
You were asking from the start. Yeah. I think someone dropped it. What did you say?
good drugs. You got
I'm sorry.
Your hands. Your hands.
It's
Right, so everybody, okay, let's put this out. We have thionyl chloride, right? Thionyl chloride, aka chloroethene, and we have polyphenyl chloride. Yeah. And then let's fill this out. Ethene means 2 carbons. Okay, ethene means 2 carbons, and these are the 2 carbons. That means the rest must be hydrogen. So the rest, must be hydrogen. So H here. So for no more carbon. Okay, and yes.
What happened during break?
What time?
happened during break? What did you do?
nothing.
No, you don't have to break anything.
Oh, that's what you explained during break.
Yeah, do you explain anything in break time?
No.
Okay.
Okay, right. Is everyone back?
No.
Make the breaks are so.
Oh, yeah.
Okay.
What hurts?
Oh, she went to the BBC. She vomited. She said.
Ooh.
Me too, sir.
So,
only if you're extremely unwell to the point that you are dying.
Never
Someone
die.
kills
Sort
me.
of like that.
Someone kill me. Come on. Okay. Right. Let's just continue. So we have styrene here. So remember, styrene is the thing with that very fancy benzene ring. Yeah, and the benzene ring has like 6 carbon. Okay, like that. And then you have H's on the sides. And be careful when you draw the polymer, okay, because that's when you have to always make sure that at least one of the corners of the hexagon aligns with this carbon. Remember? Okay, what kind of structure is incorrect? Remember this incorrect structure we drew last time? Yeah, we don't draw that because in this structure, the carbon here is not aligned with any of the carbon in the hexagon, which is incorrect. Okay? Yeah, this type of detail, you have to draw it to know it. Okay? So this is polystyrene. And then we have polychloroethene. So polychloroethene, you can make sense of it better. What does chloroethene mean? There's a chlorine. And how many carbon are there? What does ETH mean? Meaning each, that means there are 2 carbons, okay? And these are where the 2 carbons are at. That means the rest must be hydrogen and 1 chlorine. And just like before, when we put the chlorine, doesn't matter. You can put any of these 4 corners, as long as the other are hydrogen. Right, so finally, we have polytetrafluoroethene. Has anyone heard of polytetra? Trust me, you have this thing at home. Teflon. Do you have non-stick fry pan? Yes.
But the non-stick is not non-stick.
Well, that's because the coating has come off, and you should change it. Or you should replace it. Because if you do not replace it, you might be eating the coating. If the non-stick fry pan, things start to stick on your non-stick fry pan, it's not working. The coating is gone. Yeah, it's carcinogenic, meaning it can cause cancer. Okay? Yeah. So you have put this word down. And just like with perspex, if you ask me to pick between polytetrafluoroethene, calling it polytetrafluoroethene or Teflon, I would go with Teflon any day. Okay, Teflon. It means the same thing as Teflon. But of course, you can call it PTFE as well, which is actually not helping because Teflon is not on the book, but they can give you that. Okay, yeah, they will show you. I will probably ask you this in the test. Okay, so tetrafluoroethene. Can you tell me how many carbon there are? 2. That means these are where the carbons are at already, and there are only 4 positions left. What does tetra mean? 4. Yeah, remember some of you said quad means 4. Yes, quad obviously means 4, but here in organic chemistry we use tetra to represent 4, and these are where you put the fluorine. There are no other places the fluorine can go other than these 4 positions, right? So you put the 4 F's here. So this is this is Teflon, okay, or PTFE. So you have tetrafluoro. Yeah, of course you will be asked questions about like plastics that you haven't learned, but it's just the same principle. And I'm just using these many examples to prove a point. No matter what monomers are given in exam, you really have to just put the C-double-bond at the center of the state, and you can predict any polymeric structure from that. Okay? And then, finally, I think we have just 2 plastics left, okay, both of which appears on the textbook. They are perspex, okay? Does anyone remember? But if you are not look, please don't look at the notes, okay? Yeah. What is the other name of perspex? It's actually methyl 2-methyl propanoate. Yeah, methyl 2-methyl propanoate. So put it down, okay? So polymethyl. So the first methyl doesn't come with a number, okay? The second methyl has a number in front. So polymethyl, and this is an E, not an A. So propanoate. We have the space. We don't need a hyphen though. We need a space. Okay. Yeah. This is why not? That's interesting question. Why not? Will. Yeah. Where have you been?
Frame. What? I thought it's at lunchtime only.
Break was over like a long time ago.
Yes,
So make sure you come to class on time.
Chemistry grammar. Is it?
Yeah, like chemistry grammar, Okay, you will learn that again in essays. Okay, but the method, two method will This is an ester. Do you know what esters are? Heard of it before? No. It is some scent molecule. They have pleasant smell. They are used in perfumes, in food flavoring. You know those, you may have tasted some very artificial tasting cakes, right? Or cookies. They are flavored by ester. Ester is the group molecule we add to food to give you a certain sense of certain flavor. Right, so for this this is known as perspex, okay, aka plexiglass. Okay, so plexiglass. And we seldom refer to it as like a PMMP, okay? We tend to refer to it as perspex. It just sounds so much easier to remember. And then the structure looks like this, okay? And finally, we have one more here. So perspex has similar optical clarity to glass. So similar optical clarity to glass. Therefore, it is used as a glass substitute. Where glass may not be suitable, like in the making of eyewear, okay, we use perspex, okay? So similar optical clarity glass we use as a glass substitute, like in car headlamp. So car headlamp. And number two, safety goggles, okay? So safety goggles, don't spell Google, okay? So goggles here. And then the structure will look like this, okay? So you have C, O, CH3, and then you have CH3, H, and H. Remember what these groups are called, okay, and why they are at this position. You can swap the position of these groups if you like, but the two H's, they must be on one of the two hydrogen, one of the two carbon. Both hydrogen must be connected to the same carbon. Okay, you cannot have the H here and the CH3 here swapping position. So, you either put these two groups onto the right and you put these two groups on the left, or you swap them. You can't have them like mix and match like that. Okay, yeah, so let me just get rid of this first. Yeah, so we have, you should highlight that again. The first methyl here describes this one. The second methyl group here, 2-methyl, describes the methyl group at the second carbon. Where is the second carbon? This is position number 1. This is position number 2. This is position 3. So methyl, 2-methyl, and then finally you have the propanoic carbon. Okay, so this is the what color should I use here? So this is the propanoic. Okay, in because there is a double bond. So in because of the CC double bond. Right, so now it should be relatively easy to draw this. We have H, so we have H, CH3, and COOCH3 like that. Is that clear? Okay, so finally we have to wrap things up in this chapter, polypropene. So polypropene is obviously made from propene. Propene has how many carbons? Ethene has 2 carbons. Propene has 3 carbons. So the double bond carbons account for only 2 of the 3 carbons. That means one of these corners must have a carbon. Yeah, so you can put it any way you like. I just like to put things on the top right corner for some reason. And then how many H's? Yeah, there should be 3 H's. And then for this C, there should be also 3 H's on it. Because carbon always forms 4 bonds. Okay? Right. Now, you straighten up the bonds, and then you get CH3 like that. So this is polypropene, or PP. Okay, so PP. So we have here, like PUP. So this is the first P and second P. Right. This is used in the in those plastic. You know, there's some plastic that makes a lot of noise when you fiddle with it. Like maybe you have those like well, you might take away the disposable utensils. They come in those plastic bags. When you make no, this is not as noisy as bubble wrap, but it is used in. I don't see bubble wrap. I haven't seen bubble wrap for quite some time now. Okay, because the gas
the
will
bigger ones now. The big.
So how do they make those?
by forcing some air between two layers, and then they press the two layers together. Yeah, kind of like making those egg puffs, the egg puffs. Yeah, so you have polypropylene now. And that concludes the organic chemistry chapter. Okay? Yeah, so we will have the test on organic naming, reaction, exercise. Yes.
So you need the
You need what?
exercise.
The exercise. I'll give you the exercise on the next lesson on that. But the naming part is more important. The naming part is more important.
Also, can you give us the answers for next?
Yeah. Maybe
It's 2 weeks ago.
yes.
I
Okay.
did it during.
So this is propene. And now we will start another chapter which tests your understanding of other concepts.
Like,
The drawing of molecules. Okay, I hope you love molecules because in the next part we will be drawing molecules. Like what does CO2 look like? What does H2O look like? Anything.
I like this one.
No, it's a double bond, right?
There's no math.
No math. No math.
There is math. There is math in every part of chemistry except organic. I don't see any math in organic. Do you see any math? No.
Yeah.
But this
Yeah.
is very
I see
complicated.
it. That's math.
yeah.
This is.
Well, if you consider counting count as math, then everything in life is math. Because it's just counting.
Math as well.
Okay, next up we have microscopic world 2. Okay, so microscopic world 2.
Last minute chemistry facts.
Right. Okay, so for microscopic world 2, we look at the molecules, okay, the structure of molecules. Does anyone remember the definition of molecule? When do you say that something exists as molecule? When do you say something does not exist as molecule?
It's chemically bonded.
Multiple atoms. But then about these atoms, they must all be non-metals. They cannot be a metal in a molecule. Okay? Yeah. So okay, for example, for this now, a molecule is a group of atoms. Okay, these are no ordinary atoms, but a group of non-metallic atoms. Where do you find non-metals on the periodic table? On the left or on the right? On the right hand side of the periodic table. So a group of non-metal atoms bonded together. So you cannot find a metal atom in a molecule, trust me. Okay, so bonded together. So NaCl, they are not molecules. Fe2O3, they are not molecules. Anything with metal inside cannot be considered as molecules.
So what's a group of mental atoms?
What about metal atom? Metal atom, they are also not molecules. As long as there's a metal, it cannot be a molecule. Metal atom would just be metal atom. Yeah. So you can think of molecule as like a group of atoms. That has to be all non-metals. Okay? So bonded together. Let's write down some examples. And write down where we will find non-metallic atoms. We find non-metallic atoms here. So note that semi-metal also can form molecules, okay, if you're wondering. Okay? So semi-metals such as silicon, silicon, okay, may also form molecules. It's just that metals do not form molecules. Na do not form molecules, but metals right now, metals cannot form molecules. So these are the elements that can form molecules. So you have this is one color, non-metal atoms here. Okay, put down a few examples that you must have heard of. CO2, so you know we have carbon dioxide, we have water, we have methane, and at the end of this chapter, you'll be able to describe the shape of each and every of these molecules. So, but I just want to check that you know the name of these four.
Carbon dioxide. Water.
No, I already said in the break. You go to the washroom in the break or you don't. I already said at the break. Everybody hear me, right? Yeah. So and we just a few minutes past break. Okay. So nobody go to the bathroom. Okay. We have carbon dioxide. Can you draw it? Okay. So you have C and then O2 like that. Okay. Or we will draw.
That's like hurt.
Yeah. Oh, this is actually the 3D space filling model. And of course, in the exam, I will ask you to draw this. Okay, so we have this in here. So yeah, you have carbon dioxide. So you can see that this is like the carbon atom in the center, and you have two oxygen on the side. We can also toggle space filling. Yeah, this is when we like blow up the atom like a balloon. Okay, yeah, and then you will see this, and we can also revert back to the 2D structure. So you see this is the CO2. And you see the whole app. The whole app is called molecule. So you see all these are molecules. And not a single thing in here contains a metal. They are all made of non-metals. They are drugs, okay, that you know you have heard of. For example, aspirin. Do we have aspirin here? So do you take aspirin? Painkiller. So this is aspirin. There is not a heavy metal atom that you see in here. You see, there are like a bunch of C's, H's, and O's. That's molecules, okay? And that's how many molecules you have in everyday life, and there are more. There are not in the app. So you have H2O. So H2O will look like this. Oops. So we have H2O. So at the end of this chapter, you will learn to draw these. You will learn to draw these models. Yeah. So write down all these models I call now. These are called Lewis structures. So Lewis structures. Okay, named after the scientist who you can say invented this one to represent molecules, Lewis structures. And this middle thing in here, we call it the space filling model. You will never be asked to draw the middle one. So the space filling model, but it looks less scary to me. Okay, so the space filling model. And of course the one on the left will be the chemical formula, the molecular formula. Remember the molecular formula shows you the actual number of atoms. So the molecular formula here. Okay? Right, and then for CH4, I'll just draw this very quickly. So you have CH4 like that, which is C at the center surrounded by 4 H's. Finally, you have NH3. That looks like this. Okay, like the cat's paws. Okay, so you have NH3. Okay, right. Okay, then let me just draw it like that. So you have NH3. Right. These are called Lewis structure. When you look at Lewis structure, you should notice something. There should be something that is immediately obvious. Is that? Sorry?
No metal.
Yeah. Not only are there no metal, but you should see two different types of lines. The first type of lines, they are found between atoms. Anytime you see lines between atoms, we call these bond pairs, bonding electron pairs. They are the electron, as the name implies, involved in a bond. A bond is a connection, and a connection can only exist between two atoms. So these are called bonding pairs. They are also electrons that they are not involved in a bond, which we call non-bonding pair. And these are shown on the side of an atom. They are not involved in bonding. Okay, so I need to distinguish between these two types of electron pairs. So write down. There are two types of electron pairs. First, we have the bonding electron pairs. And we have the yellow non-bonding electron pairs. So non-bonding electron pairs. So you will find both, okay, or just the bonding electron pair in molecule. So the least that will appear in molecule is bonding electron pair. You may not have non-bonding electron pair, but you must have bonding electron pair. Can you look at CH4? Do you notice that it has bonding electron pair, but it has no. Do you see any yellow stuff in here? No. Yeah, so that means having bonding electron pairs, that's a must. But whether a molecule has to have non-bonding electron pair, that's optional, okay, depending on the molecule. So now, the math part that more of you hate is here, okay? How do we draw? Do you remember learning how to draw electron dot cross diagram? Yeah? Do you like drawing those diagrams? The circles, the dots and cross. Do you remember learning that? Do you enjoy drawing that? Yes. Well, then you will enjoy this chapter as well. So, okay, let me draw out the electron dot cross diagram for each of them. So, electron dot cross diagram. And you will start to know why we tend not to draw electron dot cross diagram in the exam. Because when the molecule grows more complicated, it is very difficult to see things clearly, you see. So we have dot cross, dot cross, dot cross, dot cross, 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 and then another two pairs of crosses here. What am I doing? I'm actually showing you how many electrons there are in the outermost shell of electrons. So let me put this down first. How to draw this? Well, first of all, you need to find the group number of each atom. Does anyone remember to which group does carbon and oxygen belong? Oxygen is group 6. Carbon is group 4. Carbon is group 4. Okay, that's because carbon with atomic number 6 has electron arrangement 2, 4. And oxygen with atomic number 8 has electron arrangement 2, 6. And that implies that carbon has 4 outermost shell electrons.
It's 2, 8, 8.
You mean the maximum? Yes, the maximum allowed, okay? But then we're not looking at the maximum allowed here. We're looking at how many electrons there are in the outermost shell. For carbon, there are 4. We will represent it in, using one symbol. Okay, so for example, I will represent these electrons as dots. But it's up to you. You can make them crosses if you like, okay? Or you can invent your own symbols like triangles, okay? But I think dots and cross are the easiest to draw, okay? A dot and cross. So we will draw them here. But what do we have to pay attention to? You must not show more electrons than the atom has. For example, carbon, like you see, carbon has only 4 electrons in the outermost shell, which means in the entire diagram, there can only be 4 dots. There cannot be more than 4 dots, as that's what carbon is allowed to have. It's just 4 outermost shell electrons. And by the way, you should have noticed that we only show the outermost shell electrons. Okay, so show only the outermost shell. You see, I did not bother writing down how many electrons there are in the first shell. We don't have to do that. Okay, so this is a very important point you must put down. Show only the outermost shell electrons. Okay, right. Now look at oxygen. Oxygen has 6 outermost shell electrons, which means there should be 6 crosses. Okay, so and if you count, just focus on this oxygen. You see 1, 2, 3, 4, 5, 6. So what's the difference between putting electrons outside the overlapping region and inside the overlapping region? When you put electrons in the overlapping region, those are the bonding, those are the bonding electron pairs, you see. And those you put on the outside are the non-bonding electrons here. Do you see the relation between these two types of structure? Yeah. And just like I always say, because I like to write the least amount of things as possible, okay? So this structure is way simpler, right? Yeah, I mean, if you draw this, maybe the whole structure is completed in 10 seconds. But this one, maybe 30 seconds, okay? And it gets worse, especially when the molecule grows larger. If you have to keep doing this, if you have to draw the electron cross diagram every time you're given a molecule, you will not have time to finish other questions. So this is why sometimes we like to draw Lewis structures, okay? Yeah, I'll teach you how to draw this. But this one, you have learned in Form 4. Do you know why there has to be 4 in here? Why not just 2? It's to make sure everybody has a full means 8 outermost shell electrons. But for hydrogen, full means 2. Hydrogen full means 2, which is what we will come to next. So, can you do this? here's a short exercise. We have oxygen again. So for oxygen, you don't have to copy this again. Yeah, I'll just copy it for you. Yeah, what about hydrogen? So hydrogen has atomic number 1, which means the electron return is only 1. Okay, and it has 1 electron. So can you show me what the structure of H2O should be like? Yeah, using this. So you have 1 outermost electron. So we will represent it as dots. Can you show me the electron dot cross diagram of water? Yeah, just so I know if you know how to draw the electron dot cross diagram, if you know how many electrons to put in the overlapping space. Right, note that hydrogen has only 1 electron, so you can only draw 1 dot. Oxygen has 6 outermost shell electrons, so you can draw 6 crosses. And there are 2 H's and 1 O in this relationship here. So you can try. Right, put electrons into these 3 circles. Note that there are overlapping regions in there. Whenever you put electrons in overlapping region, you mean they are forming a bond, and those electrons are shared electron pairs. So what do we put? What should we put? 2 electrons. But should they both be dots or both be crosses or 1 dot, 1 cross? 1 dot, 1 cross. You know when you share electrons, when you share something with somebody else, that thing belongs to both of you. Okay, yeah, when you share a book with your classmates, now both of you get to read the book. Okay, so same thing here. Why is it that these atoms have to share the number of electrons you see in the diagram? That's because what they do, can you count how many symbols appear in this green circle in total? I don't care what symbol it is, as long as there's a symbol, it counts. 1, 2, 3, 4, 5, yeah, 8. 8 is the magic number, right? It's the octet number we see. And not just for the oxygen on the left, but the carbon at the center and the oxygen on the right. They all have an octet structure. So how do we know if the electron number diagram is correct or not? Easy. We just have to check if all atoms have a stable octet. Okay, so stable octet, octopus. Okay, so oct means 8 here. 8 electrons in the outermost shell. This is a sign of stability. Any molecule with atoms having octet, structure would mean this is a stable structure. All the atoms are happy. I need to think of being stable means being happy. Okay, so molecules they will try to satisfy every atom, so and make sure that everybody is happy. But is hydrogen happy now? Yes. You know, hydrogen doesn't need as many electrons as other atoms. Hydrogen is happy as long as you give it 2. So you have 2 in here. But other atoms than hydrogen, they will need 8. So what is missing in the diagram? 4 more crosses, because we have decided. Make sure you make up your mind. Once you have made up your mind and you say dots represent hydrogen, you don't assign things randomly. Okay? Yeah. But you don't have to tell your teacher that, oh, I'm making dots, hydrogen, and cross the electrons of oxygen. They will know. Just make sure you don't swap the numbers around. So you have crosses, like that. Okay. So how many bonding electron pairs and non-bonding electron pairs are there? 2 bonding pairs and 2 non-bonding pairs. We describe electrons as pairs. We seldom see electrons single out, even though it's possible in chemistry, but it's very rare, an event, okay? So we actually saw the unpaired electron before in the radical. You know radical? Radical is in the organic chemistry chapter.
Yes.
Free radical substitution. Yes. Okay. I'm a bit concerned. Well, maybe that's something that everybody should improve on. Okay. So next up, we need to look at how to draw Lewis structure, because to me, Lewis structure is a lot simpler, which is why I like to draw this structure first in the exam. So below is how you draw that. So how to draw, there's a lot of math in here. So how to draw the Lewis structure. But it's just simple multiplication and addition, no longer from in here, don't worry. So how to draw Lewis structures. Remember 4 steps. It's a 4-step approach. Step 1 is to sum up the total number of outermost shell electrons. Okay, outermost shell electrons. Step 2 is to assume that all atoms obey octet rule. Figure out how many electrons there are in the outermost shell. So assume that all atoms obey octet. Find the total number of outermost shell electrons. Don't worry, I have examples on the right to show you. And then we are not done. 2 more steps to go. Step 3 is to take the answer you have from step 2 minus the answer you have in step 1. That will give you the number of bonding electrons. Okay, so, and just one more step, bear with me. So the number of bonding electrons is equal to the answer in step 2 minus the answer in step 1. Lastly, we have to find the number of non-bonding electrons. Yeah, so step 4, because in the Form 4 classroom, the yellow color cannot be seen clearly on the screen. So the number of non-bonding electrons is found by you subtracting the answer you have from step 1 with the answer you have in step 3. Okay, if you remember these rules, you can draw 99% of the molecules in the exam. Okay, I said 99 because they are molecules that break the rules. It's like they are students who break the rules. Okay? So, but most students, just like most molecules, they obey octet rule. So let me add a correction here. When I say how to draw Lewis structure, I mean how to draw Lewis structure of molecules that obey octet rule. The 99% of the well-behaving students, okay? So molecules that obey octet rule. Unfortunately, there are molecules that will break the octet rule, and these rules do not apply to them. And you have to memorize them as an exception. Okay? Yeah, but don't worry, 99% of molecules, you can solve it using this method. Let's start. We have, so let's see if we can get these structures back, okay? We will use H2O and NH3 as an example. So H2O, NH3. Can you tell me, based on the fact that hydrogen doesn't belong to any group, you know hydrogen doesn't belong to any group. When you see it on top of group 1, it's just that the author wants to make things look a little bit more tidy, okay? It's not really because hydrogen is part of this one. Yeah, because it's not metal number 1, and it doesn't have the same property as the metal. It's not shiny, it's not conductive. There are many things that metals have that hydrogen do not, so it must not be classified as a group 1 element. So you have group 6 for oxygen. Can you sum up the total number of outermost shell electrons? Hydrogen has how many outermost shell electrons? 1. Oxygen has how many outermost shell electrons? 6. Because maybe you have mixed up group number with atomic number. Okay? So this is 1 times 2 plus 6 times 2 because there are 2 hydrogens. Right, so 8 electrons. Now can you do this for ammonia? Nitrogen belongs to group 5. Hydrogen, no group again. I want you to hear something about the 8 for that quick. Okay? So 5 plus 1 times 3 gives 8. Next up, we need to assume that all atoms obey octet rule. Okay? And for this step, you need to remember that hydrogen wants 2. So hydrogen wants 2. And all other atoms wants 8. So all other atoms want 8. So remember these 2 things. And let's do this. If hydrogen wants 2 and all other atoms want 8, what is the number of electrons that the atoms will have after they obey off their rule. Hydrogen wants 2. So 2 times 2 plus 8. Because oxygen wants 8, right? And hydrogen wants 2. So you can say the calculation is quite similar to what we did on top, just that we are not using the number as defined by the group number, but the number they want us to have. Okay? You can think of step 1 as something that you do to calculate how many electrons and molecule really has, what you really have. And step 2 is for finding how many electrons you want to have. Okay, you want to have. Okay, let's say this is how much money you have. This is how much money you want to have. They're different. Okay, this is the reality and this is the ideality. Okay, you want ideally this amount of electrons. So this gives 12 electrons. I want you to do this for the second molecule. And what should I put in here? Don't do the math in your head. I need to see the expression.
8 times plus 3, but
8 plus
1 times 3.
2 times 3. Because hydrogen wants 2, other atoms wants 8. Right?
Use it as a full.
Yeah, you use the full number to do your calculation. To do yeah, this is what they want, what they strive to get. So, can everyone follow first? Yeah, let me put this back in here. What is 8 plus 2 times 3? Mental math? No. 14, yeah. You can just make calculator. So 14, yeah. So, don't worry, yeah. We'll just make a mistake, right? Yeah, so step 3. Use your calculator from this point on. Can you take the answer from step 2, subtract the answer of step 1 from it? 4, yeah, so you have 12 minus 8 equals 4 electrons. How many electrons are needed to form a bond? Let's see, this is a bond. How many electrons are there in a bond? 2, yeah, so this is another very important note that you must put down. Every single bond, every bond you see is made of 2 electrons. So that means if you have a single bond means 2 electrons. And of course we have more intense bonds than single bond. We have double bonds. We have triple bonds, which are all multiples of 2. So double bonds will be 4 electrons. Triple bond will be 6 electrons. So these are all bonds that you can extract out of a molecule.
So triple bond is the highest, right?
Triple bond is the highest. Yes. Why?
Why, sir?
Why? Because if you form a quad, let's just imagine that in an alternate reality, in a parallel universe, we have 2 atoms forming a quadruple bond. Okay, then these atoms, okay, if they are to form bond with other things, like maybe let's say there's a B in here, this will immediately break octet rule. Why? How many electrons are there in here? Let's count. We have 2, another 2, another 2, another 2, another 2 here. We have 10 electrons in total. So this will break octet rule if you have a quadruple bond. Yeah, so this I would say is the explanation I will give when you ask why are there no quadruple bond. So triple bond is the maximum. Triple bond is the maximum. So we have it in here. 4 electron means how many bonds? 2 bonds. Okay, now use your calculator again. No mistakes. So can you tell me how many bonds are there in N3? 6 electrons, which means 3 bonds. Note the difference between electrons and bonds, they are not the same. But you can get one from the other by dividing it by 2. Okay? So you have 14, that's why I said there is still a lot of math in here. Okay, but they're simple math. So you have 6 electrons, which translate to 3 bonds. Yeah, and then when you divide by 2, you get that. Now, finally, you also have to do this by, by the calculator, using calculator. Can you take the answer of step 1? Subtract the answer from step from it. This should be step 1 minus step 3, my bad. Step 1 minus step 3. Sorry. And that means 8 minus 4. You cannot take two different unit things and subtract them. For example, can you do 8 electrons minus 2 volts? No. Can you do 10 apples minus 2 oranges? You cannot. You can only subtract things that are of the same unit, right? So this is why you will be doing 8 minus 4, not 8 minus 2 bonds. They don't have compatible unit, you see. So you have to be extra careful here. So write this down. You have 8 minus 4. So minus 4. The 4 is from here. The 8 is from here. Yeah, which is 4, yes. Okay, yeah. So you have 4 electrons. What do we call non-bonding electron pairs? Write this down. They are also known as lone pairs. They are called lone pairs because they are not involved, and they're lonely. They're not involved in a relationship. Okay, you see they are on the side. They just want to just stand there. Okay, there's no partner here. They are lone pairs. Okay, this is what we call it. Every lone pair has 2 non-bonding electrons, which is why now we can divide this by 2 to get the number of lone pairs. So we have 2 lone pairs. Right. What about for the right-hand side example? 2 electrons, which means how many lone pairs? 1. Yes. So put down the calculation. You have the answer from step 1, 8, minus the answer from step 3, 6. When you subtract them, you get 2 electrons, which translates to 1 lone pair. Now, how does this help with the drawing of Lewis structure? Well, we will see. You only need the answer from the last 2 steps to draw the Lewis structure. Can you see we found that there are 2 bonds and 2 lone pairs, right? And we found that there are 3 bonds and 1 lone pair for ammonia. So let me put this down. H2O has 2 bonds and 1 lone pair. So you will learn to appreciate this method more than this one. Because in this, like the electron dot diagram, I don't know how you learn it. But the way I learned it, the teacher said, oh, just draw, you know. And I'm so, how do I know if you're not using it? Okay. Yeah, so this is why I will not teach you that method. I will not ask you, just draw, you will know. How do I know if I didn't learn, right? So you can put this down. This is how you know. We know 2 pieces of information about H2O. Number 1 is that there are 2 bonds. We found it from here. We also know that there are 2 lone pairs. And now, we put the H and the O next to one another first. What did I say? Like a bond should be found. Where are they found always? Should they be found on the atom on the side, or should they be found between atoms? Between. That's what a bond means, right? When you form a bond with somebody, it means you connect to somebody. So the H's must be connected to the O through the 2 bonds. And we have used up all the 2 bonds. We have checked this requirement. Yeah, it's kind of like somebody tell you something about H2O. Okay, here are the information we know about H2O. We know there are 2 bonds. We know there are 2 lone pairs. Use this information to draw H2O. We just check the first requirement. Now we just need to check also the second requirement. Wow. Oh, I think I wrote it wrong. It's 2 lone pairs. I copied the number wrong. This is just 2 lone pairs. Now, you can use a pencil. Yeah, you can use a pencil to draw these circles first, to keep track of the electrons. How many electrons does this circle with hydrogen contain now? What does the line represent? 2 electrons. So hydrogen is happy, it's stable, it's done. You don't need to add anything else. This hydrogen is also happy because it also has 2, right? So I will draw a happy face here showing that it is stable. What about the middle oxygen? Is it happy now? No, not yet, because it only has how many electrons in total? 4. Do you see where the 4 electrons are? This represents 2 electrons. This represents another 2. 2 plus 2 means 4. 4 is 4 from 8. That means we will add the remaining 2 lone pairs here. Yeah, you can put it anywhere. You can put it here. You can put it anywhere like that. Okay, but it just doesn't look nice. Okay, so we tend to draw it symmetrically like that. Okay, just like in organic chem. That's the Lewis structure. And you can easily translate this back. Don't you see? This is the same thing as this one. Just that it's more simple, right? Can you see that? Now, let's try to draw the ammonia's Lewis structure. Look at what we have now. We have 3 bonds one lone pair. So write this down. NH3 has 3 bonds, 1 lone pair. That we know. So I'll leave that to you now. Okay, so 3 bonds, 1 lone pair. I will show you the whereabouts of the atoms. You tell me where to put them, because there's only one way to put them. Only one way to check both requirements.
Straight line.
This, maybe
Where does the yellow lone pair go?
on the
On the top of N. On the top of N, right? So do we all agree? So check to see if this is the structure you are referring to. Doesn't look like Sarah's to me. Yeah. There's a bond. There's 3 bonds, and there's 1 lone pair. How do you know this is the right structure? Again, yeah, you don't have to draw these circles, but I draw the circles at first to help you keep track of the electrons on each atom. You can see that for this H, there are only 2 electrons in this circle, which makes it happy. This N has 8 electrons, contributed by 3 bond pairs and 1 lone pair. And this H and this H, they are also stable. Yeah, it is with this equation. I wish I had learned this method earlier, but back then when I learned this, the teacher just asked me to draw, and I actually draw enough to finally know how to draw it. But that's not the way I wanted to learn. I wanted to learn this method, and then you can convert this back into this structure. You see, they're the same thing. You see, okay, and you can translate this back into the electron dot cross diagram. So let's do that now. After you have drawn these 2 structures, we can then convert this back to the familiar one. We know this one. But honestly speaking, I really hate drawing this because there's so much stuff to put in this structure when they represent the same thing as this simpler structure, right? Yeah, so it's just a hassle to draw. But anyway, if in exam, in the event that you're asked to draw it, you can first draw the little structure using the method on the left. This method will for sure give you the correct answer. You cannot get a wrong answer. Well, the only way to get a correct answer is you type the wrong number on the calculator, but that's on you, okay, not on the method. Okay, and we have, you have in here, dot cross, and then you put cross. You see? Yeah, how do we translate this little structure back into electron dot cross? We put, yeah, it's up to you to define the symbol. You can make these crosses if you like. As long as you say so, if nitrogen is cross, then hydrogen will be dot. Is that clear? Okay? To check that everyone can follow, I have this example on the right, on the next page that I want you to work on now, all of you. Okay, I'll give you the group number. Okay, don't worry. We have C2H4 and N2F4. Okay, I want you to use the method. I'll show that on the screen in case you haven't copied that. Okay, I'll show the method on the screen. Copy these 2 formulas first. N2F4 and C2H4. I will tell you the group number. This is group 4. In the exam, this is you who look it up. Okay, nobody would give that to you. So this is no group. This is no group. So this one belongs to group 5. This belongs to group 7. So copy the group number, copy the formula, and then I will show you the rules. And you use the calculator. Okay? Right. Yeah, no excuse making mistake if you're using a calculator. Okay, so we have, let me copy this over. So you may start now. We can check, we'll check the answer in 2 minutes. I think 2 minutes should be enough for just 2 simple structures. So you can refer to these rules on the left now. Yeah, continue work on C2H4 and N2F4. So I see that some of you have got the correct expression, okay, but then maybe in the calculation, okay, there might be some careless mistakes, so just be careful. Can somebody tell me what's the number of bond pairs for C2H4?
6.
They are, 6. And then are there any lone pairs?
0.
0. Does everyone get the answer? If not, check to see which step went wrong, okay? So we have 4, let me write down the answer. 4 times 2 plus 1 times 4. So you can write this like this. C2H4. For the second step, we assume that all atoms obey octet rule. So we have 8 times 2 plus 2 times 4. So 8, 2, 2, 4. So the first one would give 12. The second one would give 24. The first step would give 24 minus 12. So 24 minus 12 is 12 electrons, which translates to 6 bonds. Right? Lastly, when you check these two numbers, you see they are equal, which means the answer to the last question can only be 0. So, and it's okay to have 0. Remember what I said? A molecule must have bond pairs, but it may not have lone pairs, right? So it's okay. You no need to panic. We have 0 electrons, so 0 lone pair. Now, we have C2H4. Let me show you where the atoms are at, and you tell me where to put them. Where do you put 6 bonds? You can try. You can try. And here's an additional tip. What kind of bond will hydrogen always form? Can hydrogen form triple bond? Why not? Because it has only 1 electron. Remember when I share electrons with you, when I share something with you, both of us contribute equally, right? If we have to share 2 electrons, I will give once, you will give once. When I form, sorry? No. I already said before the recess, nobody goes to the toilet. Okay? So if we are forming a double bond, then I will donate 2, you will donate 2. Every time it has to be an even contribution. So hydrogen, because it has only 1 electron, you can only put 1 bond in between. Like that. How many bonds are left unutilized? You have 6 bonds in total. You have 2 bonds unutilized. They must go here. What is this? You just learned it in the previous chapter. Ethene. Yes, ethene. And because there's no lone pairs, this is the correct structure. Write down the name. You should know it. I mean, if you don't know this bad, okay, you can watch the organic chemistry. That's why I do video. No more excuse for any one of you for not, like, for this in the class, doing, I don't know, yeah. Okay, next up, see if you can get the second right. Anyone can tell me what's the answer to the first step? Yeah, I need the expression because I'm worried that you will get it. Yes, 38 electrons. So you have n times 2 plus f times 4, 7 times 4. Next up? Yes, or you can just do 8 times 6. 8 times 2 plus 8 times 4, which is 48. What is 48 minus 38? 10. Which translates to how many bonds? 5. So, you see, this is much better than just guessing. With that method, when I first learned it, you just guess, just try 1 or 2 and 3. Okay, well, if I have to guess, I don't have time to finish other questions. So this method will get you to the answer right away, straight away. So you have 5 bonds. Finally, how many electron pairs are there that are lone pairs?
14.
4. There are 14. Okay, 14. 14. Okay, let's see where they put it. So you have 38 minus 10. 38 minus 10, which translates to 28 electrons, which translates to 14 lone pairs. It may sound scary, but you can draw out the electrons that are bond pairs first. So we have 5 bonds. Yeah. I'll show you the framework, okay, and you put the electrons where they belong, wherever they should belong. So you have nitrogen, F, 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 F. So where must the 5 bonds go? There's only one way. Yes, one in each position, right? I mean, unless you can think of another way. Okay, yes, this is the only way. What about the 14 lone pairs? Check to see if everybody is happy with what it has right now. If they do not have what it has to be happy, they will need some extra lone pair. So you tell me, if you haven't got this structure yet, draw this out. I will give you 30 seconds to show me where the 14 lone pair should go to satisfy everyone, to make sure that everybody is happy, everybody has a stable octet. 30 seconds. It shouldn't be hard, okay? Just remember that all items should have 8. All items should have 8. Structure. You are close, but you don't have 14 lone pairs. You can check. You are missing some lone pairs. Yeah, but for okay, I see that some of you have got it for a structure. So again, if you're unsure, I recommend that you draw these very faint pencil lines to keep track of the electrons around each atom. You can erase it afterwards, okay? But this is a good start when you first learn the method. Look at fluorine. Tell me, how many electrons does it have right now? 2. 2 is how many electrons from 8? 6. That means it needs an additional 3 lone pairs. 1, 2, 3. Done. The same can be said for the rest of the fluorine. That will already use up 12 of all the 14 lone pairs. Where do the remaining 2 go? On each nitrogen. You can put it on top, you can put it, I see a lot of variation in answers. You can put it on the bottom, you can put it on the side. As long as this is in the vicinity of nitrogen, it's fine. That's it. Isn't that easy now? Yeah, okay. It is much easier, trust me, than drawing this. But you can convert this back. Yeah, you can try. Take out the form 4, form 3 worksheet you have struggled with. This method solve it in 1 minute. Okay? Yeah. And you can calculate with a calculator even faster. So this I don't know. I wish my teacher had taught me earlier. So now I'm teaching you this, so remember that. So you have and five C plus number 12. Plus number 12. That's number 12. Stay outside always.
It's a very
Is not present. Okay, so that's the remember the 90% of molecules that this rule can explain. There are, however, exceptions to octet rule. That I want to put that now. There are exceptions. The 90% of the problem on the textbook you can solve it. Okay, yeah. So let's see if I have the textbook on here. I think it's chapter 24. Yeah, so we have 90% of the molecule you see in here. So like CO2, okay, let's say for these you can explain fully using this method. But then the main part of this chapter is on non-octet structure. Those that violate octet rule, those students that violate school rule. So exception to octet rule. Okay? So while most atoms, when they form molecule, Yeah, when most atoms form molecules, they obey octet rule. That's what applies to most, but not all. They obey octet rule. Some atoms may violate the octet rule though. And we have two groups of exceptions. So exception group number one, the incomplete octet species. Do you know if octet means 8, incomplete means less than 8. That's all it means. Okay? So incomplete octet species. There is also something that can have more than 8. You know, if 8 is a norm, then of course there will be something that will have more than 8, something that will have fewer than 8. For those with more than 8 electrons, we call them expanded octet species. Okay, so expanded octet. You have incomplete octet and expanded octet species.
So are they still stable?
They are still stable. Yeah, but how should I put it? Okay, they cannot be predicted. I mean, the structure cannot be predicted easily using this method. Okay, but I will show you. I can adapt this method a little bit, and you can still use this method to explain those structure. Okay, let's see. Not for incomplete structure though. For expanded octet, you can explain them using the same method. But for incomplete, you must remember them all. They are exceptions. Okay, so you can say CH4. So CH4, CO2, H2O, and what else? Like Cl2. You know, these are a bunch of molecules that obey octet rule. So this is what I mean by most. Okay, these are the well-behaving students. Okay, so they obey octet rule. You can check. All the atoms here obey octet rule. They either have a full shell of 2 electrons or full shell of 8. The exceptions, though, we have. I think it's best that I draw it in different colors so we can calculate them. So we have incomplete. So incomplete octet species. So these are the 99.9% of molecules that obey octet rule. Okay, there is less than 1% of the molecule that will violate octet rule, either by forming incomplete octet species, which you have 2, BF3, BeCl2, and ALF3. Okay, so you have BF3. Tell me what is weird about BF3. Which atom is violating octet rule? Boron. B for boron. What about beryllium chloride on top? Beryllium. With only 4 electrons around beryllium and only 6. You know 4 and 6 are both less than 8. So they have less than 8. So incomplete octet means less than 8 electrons in the outermost shell. Obey octet rule means 2 or 8 electrons in the outermost shell. Okay, so 2 or 8 electrons. 2 applies only to hydrogen. Okay, so in the outermost shell. What about expanded octet? Maybe you guess it. They have more than 8 electrons in the outermost shell. And examples include SF6. So SF6 is a rather interesting gas. Maybe some of you have done experiment on that before, maybe not. Okay, you know you can inhale helium, and it will make your voice go Mickey Mouse. Mickey Mouse. There is another gas that will do the opposite. It's SF6. So you sulfur. Oh, I'm surprised. Have you inhaled that before?
Yeah, I've seen Conan O'Brien.
Well, it's a gas. Okay, let me find it first. So sulfur. Oh. You see, this is almost like a magic show.
We breathe that in.
There's a gas inside, yeah, which you cannot see. It's sulfur hexafluoride. It's so dense than air. So you see, you can treat it like water, but it's invisible. Yeah, this is sulfur
What
hex.
is that?
What?
What is
That is a gas called sulfur hexafluoride. When you breathe that in, it will make your voice very, very, very deep.
Sir, can we do this experiment?
No.
Why is it deadly?
I think if I remember, this is a toxic
They're
chemical.
so nice.
So eventually, I mean, this experiment is just like what would happen when you put a paper boat on water, right?
Yeah, it's like on.
This experiment proves just one thing. Sulfur hexafluoride is denser than air, just like water is denser than water. I mean, water is denser than air. Water is denser than air. Yeah, rather interesting term. Even more interesting if you breathe this in only a bit. If it's too much, it will still kill you. Okay. Sulfur hexafluoride. This. Let me draw this out first. You need to remember this example. Sulfur hexafluoride. But on textbook you won't find this experiment, which I think is pretty interesting. So you have sulfur hexafluoride, SF6. SF6. And put down PCl5. So PCl5. So PCl5 like that. Sorry? No. But it's also pretty dense. Yeah, PCl5 is for other uses that you will learn in later part of organic chem.
Yes, sir. 13.
Okay, yeah, if you must leave now, you can leave. So this is PCl2 and we have I'll finish this off. You have CH4, H2O, CO2, and Cl2. Just note that most of the molecules, they play by the rules. Some molecules, they don't play by the rules, okay? They violate some of the rules. So can you just circle the atoms that are like these misbehaving atoms? Okay, so you have these ones. The sulfur here is breaking octet rule by having how many electrons? How many? How many bonds you see?
6.
For phosphorus is 10. For sulfur is 12. Both 10 and 12 is greater than 8. They are both greater than 8. And both 6 and 4, they are less than 8. Right? That's why, you see, this is the incomplete octet species. Okay? They are very few. They are rare, but they do exist, like you saw in the experiment. Okay? For only the middle one, you need to memorize it by heart. The ones on the right, you can still work it out by doing something to these rules here, as I will show you. But any question? No.
No, it's not.
Chapter 24. Chapter 24. Okay?
Can you send this to the Google Class?
Yeah. But let me just. Yeah. Okay.
The
Let me
entire
just.
book.
Okay, the entire book.
Yes.
Oh, okay. Right. Let me
No, we
wait.
don't
a
need-
second.
No, that's the textbook.
The molecule F. It's just called molecule. Yeah, it's actually called molecule. Okay. Yeah. It's by like a chemistry enthusiast. Okay. Or yes. So here we have. Yeah, I'll list on the Google Classroom and then you can use it now. We'll have the I'll distribute some homework on I'll be giving answers, but I don't want to give you the answer you don't do it, because I know if I give answers, students will just say, oh, I wish I